On May 7th, 2026, OpenAI stopped letting new customers fine-tune anything at all. July 2nd took it from anyone who had gone quiet. January 6th, 2027, the door shuts for everybody. The reason they gave is the one you have probably already guessed. The models got good enough to just ask. Mostly true. But there is a short list of things fine-tuning does that no prompt can do. A prompt lives in the context window. A fine-tune lives in the weights. Those are different pieces of machinery. One receipt before any theory. A medical coding model scoring 0.39 against physicians at 0.45. After fine-tuning 0.57, it went from losing to the doctors to beating them by 12 points. And the team did not hand it a giant label dataset. They handed it a grader and let it search. Now the other side. A prompt optimizer called GEPA beat reinforcement learning by up to 20 points, using 35 times fewer rollouts. So prompting is not the underdog in this fight. It is the favorite, which makes the question sharper. If prompting wins most of the time, what is left that it cannot reach? 5 things, each one with the numbers, and then where all this work moved after OpenAI closed its door. Start with what a prompt actually is at runtime. Every request, your instructions get tokenized and pushed through the model next to the user question. Nothing about the model changed. It read your rules from scratch, the way it did the previous 10,000 times. Fine-tuning is the other move. You run examples through the model and nudge the weights until the behavior you want becomes the path of least resistance. The instructions stop being something the model reads. They turn into something the model is. A colleague with your style guide open in another tab will follow it. A colleague who has written in your house style for 2 years does not open the tab. Both produce good work. One of them is faster, cheaper, and much harder to knock off course. That difference lands on the invoice before it lands in the quality metrics. A 4,000 token system prompt across 1 million calls a month is 4 billion tokens a month, spent saying the same thing to a model that already heard it. Caching softens that. Anthropic charges 1/10 of the normal input rate on a cache read. OpenAI discounts repeated prefixes automatically once they cross about 1,000 tokens, so most production prompts qualify without anyone doing anything. But a cache is still a copy of your instructions traveling through the model on every single call. Baking them into the weights deletes those tokens entirely. There is a quality reason too, not only a billing one. In July 2025, the team at Chroma ran 18 models through a long context stress test. Claude 4, GPT 4.1, Gemini 2.5, 3 sizes of Qwen 3. Performance did not decay smoothly as the input grew. It fell off cliffs. And the closer the distractors sat to the real answer and meaning, the earlier the cliff arrived. So the instinct to fix a problem by adding one more instruction has a ceiling wired into it. Past some point, you are making the model worse at reading the paragraph you just wrote, which is the tension running through this whole video. Context is rented. Weights are owned. Most of the time, renting is the right call, and occasionally, it is the thing standing between you and a working product. Thing 1. More examples than you can fit in the window. This is OpenAI's own first argument for why fine-tuning exists, and it survived all the way onto the page announcing the shutdown, handling more example inputs and outputs than could fit within the context window. Few-shot prompting works because a handful of examples pins down the format. 10 examples, maybe 50, at 200 examples of a genuinely messy task, you are burning most of your context before the user has said a word. And the interesting behavior is rarely in the first 50 examples. It lives in the tail, the invoice with 2 totals on it. The customer who typed their address into the name field, the clause that means the opposite of what it looks like it means. Fine-tuning takes the whole tail. Thousands of examples folded into the weights over a few hours of training, and then the context window sits empty and ready for the actual job. The examples stop being something you pay to reread and become part of how the model reaches for an answer. Ambience Healthcare is the clean version of this. Their task is mapping a doctor's note onto ICD-10, which is roughly 70,000 medical codes with specificity rules stacked on top of them. You cannot prompt 70,000 codes. Retrieval does not rescue you either, because the hard part is not finding a plausible code. It is knowing exactly how specific the note lets you be. Base 03 Mini scored 0.39. The physician baseline they measured came in at 0.45. The fine-tuned model landed at 0.57. OpenAI's own write-up says it removed about 1/4 of the errors trained physicians make. Look at that ordering, because it is unusual. The starting model was worse than the humans. The tuned model was better than the humans. No prompt moved it across that line. The weights did. Thing 2, and this is the one that pays for the project. The prompt gets short. Picture a mature production prompt after 6 months of life. Tone rules, formatting rules, 9 edge cases somebody added after an incident. 2 examples nobody dares delete because they are no longer sure what those examples are holding up. That thing is 3, 4, 5,000 tokens, and it rides along on every request, whether the user asks something hard or typed hello. A tuned model does not need to be told your tone. Your tone is in the weights. The prompt collapses down to the actual task, and the token bill collapses with it. Latency drops as well, and that gets undersold. Time to first token scales with how much the model has to read before it can start writing. Cut 4,000 tokens of preamble, and the answer starts arriving sooner on every single call. There is a third effect hiding in here. Your proprietary material stops traveling. If the knowledge is in the weights, you are not pushing your internal playbook through the wire on every request just to remind the model how your company works. The honest caveat is that caching gets you a big share of the cost win with no training at all. If your prompt is stable and your traffic is bursty, cache it and move on with your life. Fine-tuning earns its keep when the volume is large, constant, and dull. That is the profile the economics reward. And it is a narrower profile than most teams admit to themselves before they start. Thing 3. You can make a small model genuinely good at one narrow thing. Biggest lever on this list, least glamorous. The shape is distillation. Take a frontier model, run it across your task, keep the outputs that survive your evals, and train a small open weight model on what is left. What comes back is a model that handles your one job at close to frontier quality, on hardware that costs a fraction as much, answering in a fraction of the time. Training got almost trivially cheap. Together charges 48 cents per million training tokens for a LoRA fine-tune on a base model up to 16 billion parameters. The minimum charge on a job is $4. $4. That is the floor on making a model permanently better at the thing your company does. Full fine-tuning at that size runs $1.20 per million. The 70 to 100 billion tier is $2.90 on LoRA. Fireworks prices the same tiers within a few dollars of that and lets you serve the adapter without renting a dedicated box for it. The method stopped being exotic too. In September 2025, Thinking Machines published a piece called LoRA Without Regret, and the finding was reassuringly dull. LoRA matches full fine-tuning when you apply it to every layer instead of only the attention blocks. Same final performance, roughly 2/3 of the compute, and a learning rate about 10 times higher than you would use for a full run. For reinforcement learning, they found LoRA matched full fine-tuning at rank 1. Rank 1 is a rounding error of extra parameters bolted onto a frozen model. The adaptation is far smaller than the folklore says it needs to be. The pattern that actually ships is a router. The small tuned model takes the bulk of the traffic, and anything it flags as unusual escalates to the big model. You pay frontier prices on the slice that genuinely needs frontier reasoning. Thing 4. Fine-tuning collapses variance in a way instructions do not. You have felt this one. The prompt says, return JSON with these 6 keys. It does, about 94% of the time, and the other 6% is a friendly sentence in front of the JSON that detonates your parser. So you add a line telling it to skip the friendly sentence. 97%. You add another line. Still 97. At some point, the instructions stopped being the bottleneck, and the model's own prior took over. Harvey, the legal AI company, ran this on citation extraction, pulling the exact passage that supports a legal claim. Their F1 went from 0.563 to 0.677. And against GPT-4o, their tuned model won, or tied 93% of head-to-head comparisons, on a task whose failure mode is a lawyer citing a passage that does not say what the brief claims it says. SafetyKit does content moderation, where the entire job is applying a fuzzy policy the same way twice. F1 from 86 to 90%. And they use the tuned model to replace dozens of separate calls in production. Milo, a scheduling product, went from 0.86 to 0.91 on overall correctness. The number I would actually care about is their hardest bucket, which went from 0.46 to 0.71. 4 points of F1 sounds like nothing until you notice what it is made of. It is the tail, the cases where 2 careful humans would have argued about the answer. That is exactly the region prompting has the weakest grip on. Thing 5, and this is the one I find genuinely strange, because it is barely teaching at all. Ordinary fine-tuning needs the right answer for every example. You are showing the model finished work and asking it to imitate the shape of being correct. Reinforcement fine-tuning does not need the answer. It needs a grader. You hand the model a problem, let it produce several attempts, score each one, and push the weights toward whatever scored well. That is a different kind of supervision. You are not describing the destination. You are describing how you will recognize it when you see it, and letting gradient descent do the searching. ChipStack works on semiconductor verification, binding design interfaces to verification IP. They tuned O1 Mini and O3 Mini on fewer than 50 training samples and got roughly a 12-point improvement on both. Fewer than 50. That works because they were not supplying knowledge. They were supplying a definition of good. And the tuned models got noticeably better at recognizing when the wiring should not be applied at all. Accordance, working on tax analysis, reported close to a 40% improvement over base models on TaxBench. Run loop, generating Stripe API code that has to actually compile, averaged 12% more total reward. Thomson Reuters ran it across 3 co-counsel skills: document review, comparison, and summarization. And the tuned model beat the baseline on all 3. It has hard limits, and OpenAI is blunt about them. If your model scores 0 on the task today, there is nothing to reinforce. If it already scores perfect, there is no signal left to climb. If your own experts disagree about the right answer, you do not have a grader, you have an opinion. An RFT runs expensive, in some comparisons, 100 times the cost of ordinary supervised fine-tuning. Now let me argue the other direction properly, because the case against fine-tuning got a lot stronger over the last year. GEPA is a prompt optimizer. It reads its own failed attempts in plain language, writes down what went wrong, proposes a rewrite, and keeps the versions that survive. No gradients anywhere in the loop. Across 6 tasks, it beat GRPO, a reinforcement learning method, by 6 points on average, and by as much as 20. Using up to 35 times fewer rollouts. It went to ICLR 2026 as an oral presentation. If a search over English sentences can outrun gradient descent on your task, then spending a week building a training pipeline is a choice you should have to defend in a design review. Fine-tuning also narrows a model. Train hard on one format, and you can lose ground on everything adjacent to it, which is why the tuned model that aced your eval sometimes falls apart the moment a customer asks something slightly sideways. A prompt you can edit in 10 seconds. A regression baked into weights cost you another training run and another week of eval. And it is a poor way to install facts. Weights are a lossy, slow, expensive place to keep a price list that changes on Tuesday. Retrieval owns that job. Fine-tuning owns behavior, format, and judgment. Then there is the clock nobody budgets for. A fine-tune is welded to its base model. OpenAI's own deprecation table retires the fine-tuned GPT 3.5 Turbo and GPT-4 families on October 23, 2026, and every custom model built on them retires with them. So owning a fine-tune means owning an eval set, a retraining cadence, and a migration plan for the day your base model gets old. That standing cost is the part that kills most of these projects, long after the launch demo went well. OpenAI clearly read the same room. By the end, supervised fine-tuning there was down to the GPT 4.1 family, and reinforcement fine-tuning to exactly one model, O4 Mini. Then the wind-down notice went out. Read that notice carefully though. Inference on existing fine-tuned models keeps running until their base model retires. What is being switched off is the ability to create new training jobs, and the work relocated rather than stopping. In February 2026, Amazon Bedrock added reinforcement fine-tuning for open weight models, starting with Qwen 332b and GPT OSS 20b, behind an OpenAI-compatible API. Together and Fireworks will tune Llama and Qwen for you by the million tokens, and Together hands the weights back so you can self-host later. Google tunes Gemini on Vertex, though the 3.x line was still unavailable for supervised tuning as of April. Anthropic never opened tuning through its own API at all. The one managed path is Claude 3 Haiku on Bedrock, capped at a 32,000 token context. So the center of gravity moved to open weights, which is a strange outcome when you say it out loud. The technique that most needs a model you can modify ended up living on the models you can actually download. Here is the rule I would use. Prompt first and prompt properly, with an optimizer if you have one. While you are still learning what a good output looks like, a prompt is the cheapest place to change your mind. Reach for the weights when 3 things are true at the same time. The shape of the task stopped changing. The volume is large and dull. And you can write down, in code, what a good answer looks like. Miss the first, and you will retrain forever. Miss the second, and you will not earn the training cost back. Miss the third, and you are guessing with a GPU. Hit all three, and fine-tuning does something no prompt is built to do. That is the list. If you build on these models, the useful question is not which technique wins in general. It is which one your particular problem has outgrown.